So with this lesson, we're talking about Euler's theorem, and let's just get that out of the way right now. You're going to see this word a lot, E-U-L-E-R, and it's pronounced Euler, not Euler or any other version. So that's why the grammar may look funny, and even Word doesn't understand that. The proper way to say an Euler circuit. Because if you make that O sound, you put an in front of it instead of a. But anyway, so we got the word out of the way. Just a little quick thing to think about. Nobody's ever sat down to do homework and thought, I've got to figure out a way to make this take as much time as possible. Ha ha, we all know that's definitely not true. With pretty much everything we do, we're looking for more efficient ways to do things. And so one of the really good examples of this kind of thing is mail routes. Or if you get into thinking about Amazon drivers or FedEx drivers or anything else, they've got to go through a certain path, hitting certain stops, and they got to do that as efficiently as possible rather than just going everywhere aimlessly. And so you want to think about ways to do that in the most efficient way possible, and that's where graph theory comes in. So the delivery locations are the vertices, and then the routes taken between them would be considered the edges. So an efficient route would be to visit every vertex, that's to make all the stops, without going over any of the edges more than once. That way you're not backtracking down a road that you've already been on. So this idea has been studied and named after this guy, Leonhard Euler, or Euler, the correct way to say it, which addresses the problem that involves tracing an entire graph without repeating any edges. So that's really the key. So an Euler path is a path, we've already studied what a path is, that passes through every edge in a diagram exactly once. An Euler circuit is a circuit that passes through every edge exactly once. So we'll look at an example, and as we do that, let's just remind ourselves, a path is just a sequence of adjacent edges and vertices that doesn't go through any edge more than once. And then a circuit is a special path that then starts and ends at the same place, starts and ends at the same vertex. So the difference between a path and an Euler path is that a path can pass through any subset of the edges on a graph, but an Euler path passes through all of the edges exactly one time. So this figure here shows us an Euler path, and I think of it this way. Wherever you start, so we're starting here at A, you've got to color in every single edge. So if we follow the arrows, we went to B, then we went to E, then we went to D, then we went back to C, then up to E. So that's a path, not a circuit, but that's a path. That's the A, B, E, D, C, E. A, B, E, D, C, E. I think I said the letters in the wrong order the first time. But anyway, you get the point. So that's a path. And notice we actually hit vertex C twice, but that's okay. You're just not allowed to hit an edge twice. And so that's an Euler path. And then this next figure shows us an Euler circuit. So that begins and ends at vertex B. So we started at B, and we went up to A, down to E, down to D, around to C, up to B, over to E, and then around to B. So there is an Euler circuit that we made it through every edge in that diagram exactly one time. And it was a circuit, meaning we ended back at the same place. So that's kind of the idea. Let's look at an example. And so what we're doing with this first question, we're supposed to complete the parts below but indicate our answer in the graph, and then writing the sequence of vertices. So we've got the sequence started in both cases, and we've got the start of a circuit in this case and a path in this case. So we want to make an Euler circuit. So that means we started here at Y, and so that means we also have to figure out a way to end at Y. So we've gone over to here, up to here, up to here, so now we're at S. And so now we've got a choice. We go a number of different places. And so it turns out you can actually do this a couple different ways and still get it right. I'm going to go over here to T. I'll go down here to Y, and then back up to S, back down to X, back over to Z, back up to Y. And so our path there, our sequence there for that circuit would be, we went, let's see, get the letters right, we went Y, V, U, S, then we went over to T, back down to Y, then over to S, then down to X, then over to Z, and then back up to Y. So there's our full sequence that gives us a circuit. Notice we completed that circuit. We started at Y, we ended at Y, and we hit every edge exactly one time. So now we just need a path. For this, we want to make an Euler path. We started at B, and so we went B to G to F to C. So we've got that much of the sequence listed. And so then just things to note, if we went down here, that would force us to do this, go back around, and now we're stuck overlapping. So that definitely isn't going to work. So we can't go down from C. So that option won't work for us. So try something else, and you can go either over to A or up to B. Either one will work. So if we go, I'm just going to go up to B, and then around to A, and then back to C, and down to D, and around to E, and up, and we'll end at F. Excuse me. So now that's a path that we've covered every edge exactly one time. Notice it's not a circuit because we didn't end back where we began, but we did complete an Euler path. The question that we'll talk about in the next video is this always possible? Is it always possible to have an Euler circuit or an Euler path? And it turns out the answer is no.